Hello everyone, my name is Nicolas Papanikolaou and I'm a PI at Sampalimou Foundation, Lisbon, Portugal. Today I would like to grab the opportunity and guide you through the results we obtained during the last 4 years working for the ProCANcer-I European funded project. The types of AI models that were developed and validated under the scope of ProCANcer-I project can be grouped into detection, segmentation, and classification models supporting the implementation of 9 clinical use cases. In addition to that, 2 models served the need to automatically identify data and monitor their corresponding quality. One important challenge at a multicentric setting, including ProCANcer-I, was the labeling process, especially when time-consuming segmentation masks are necessary to train detection or segmentation AI models in a fully supervised setting. For the latter purpose, we developed a self-supervised learning approach that eliminated or reduced significantly the need for massive human-generated labels, providing equal or even higher performance than the conventional fully supervised models in segmentation, detection, as well as characterization tasks. Starting with segmentation, state-of-the-art models to segment the entire gland, as well as the central and peripheral zones, were developed on diverse data, resulting in high performance, which may accelerate clinical workflows and may make more accurate the quantification of important prognostic biomarkers like PSA density. In addition, the generalizability of such models was thorough and evaluated across countries, imaging protocols, MRI manufacturers, providing insightful results on the type of data such models should be exposed during their training phase. Finally, both clinical radiomics signatures and deep learning-based AI models surpassed the performance of radiologists using the PI-QUAL score alone and resulted in a reduction of more than 20% of unnecessary biopsies. The secret sauce behind developing successful and clinically useful AI models relied on 3 pillars, which were big data, improved quality, and wide diversity to smooth out biases and learn invariant signal. Here is one case where a patient presented with bilateral lesions in the peripheral zone with very similar characteristics. Automatic segmentation by AI and extraction of radiomic features from the entire gland suggested that this patient has clinically significant disease. However, there is one caveat here, and it's the lack of providing information related to lesion location. For that reason, the Sampalimou Foundation Clinical Computational Imaging Group developed a novel methodology to visualize radiomic signatures by computing the probability of clinically significant disease on a pixel-by-pixel basis, producing such color maps where red means high probability, yellow and green means medium, and blue means low probability for clinically significant disease. In the previous example, these maps clearly shows that the lesion on the left is more aggressive than that on the right, which was confirmed eventually by biopsy. The same group conducted a rad path correlation prospective study where 3D printed personalized molds were generated and used to cut the surgical specimen exactly in the same geometry with MRI, making possible the side-by-side comparison of digital histopathology and AI detection models. At the end of this 4 years journey, we learned a lot, and we are grateful to the funding authorities for entrusting us and giving us the opportunity to collaborate and push further the state-of-the-art in such an exciting field, prostate cancer AI. Thank you so much for your attention.